Okay, so now we're looking at a parallel arrangement of RLC. Notice how we have the two power supply connections, or the AC source connections, connected directly to our first load, our resistive load, and then every other load shares those same terminals of the source as a parallel circuit does. So now we have the two blue wires connected to each side of the 300 millihenry coil, and then we have the yellow wires connected to each side of the 68 microfarad capacitor. Okay, so now we've got a connection of RLC in parallel, and now our voltage, which will be our 50.9 volts of applied voltage here. I'll just tweak that down a bit. Our voltage of 50 volts AC as our source voltage, will be the same voltage across each and every component. We have the same voltage for parallel. Okay, so what will be the result of a parallel connection? It'll be a current divider. Okay, so let's take a look at our total current first off. Okay, so if I put my probe on the source connection to the parallel arrangement, I'm going to be indicating my total current. And notice how my total current in this case is 1.05 amps. That's my total current. Okay. Now, if I want to measure my inductor current, remember I have to look at both the current entering and exiting. So I have to set up the clamp like this with the arrow such as this. This is where I'm summing both the current entering and exiting, and the remaining current, which will be plus current entering and minus current exiting, is going to be the current of the inductor only. So now let's look at the branch current for the inductor. The branch current for the inductor is 460 milliamps. Okay, so in order to isolate our capacitor current only, all I have to do is clamp the conductor for that last branch, and to clamp it with the arrow in the proper direction. And now we can look at the capacitive current. And when we look at the capacitive current here, notice how it's almost twice or three times the value of the inductor current. So that was 1.3. I'll go back to the inductor current here. And the inductor current is 460 milliamps. It's like 3 times the value. So that means that we have a primarily capacitive circuit. Our capacitive current is greater than our inductive current. So what that means is, now if I look at the phase angle of this circuit and the power, I'm expecting it to be primarily capacitive, and I'm expecting it to have a positive phase angle or a leading current. So notice how I set up the current probe to measure total current again, and I've got the voltage across the source for total voltage. This is going to give me total circuit values when I go to power. So I'm going to go to the power menu. I'm going to hit enter. When I do that, you can see my real power is 26 watts. That's the power being dissipated by the resistor. Notice how my total power, which is the result of imaginary and real power, is 53 VAs, and my volts amps reactive, which is my imaginary power, is clearly showing that it is primarily a capacitive circuit. Notice the capacitive symbol there. Okay, so we have 46 VARs of imaginary power. Okay, what's that going to look like then if we look at the scope menu? We're going to go to the scope menu, and we're going to go to the setup, and we're going to change this to phase now. And we're expecting a positive phase angle, which we can see here as 56 degrees positive. That means the current is leading the applied voltage by 56 degrees. All right, so that's the way you use the power analyzer to measure power, to measure phase angle, to measure branch currents in parallel, or series voltages in series, and total current in series using the current clamp. Okay, now remember, it all starts with properly setting up your power analyzer, so make sure it's calibrated and set up properly before you even take these measurements. But these are the ways in which you can measure phase, branch currents, and voltages. All right. Okay, I just wanted to do one more demonstration on using the desktop ammeter to measure our branch AC voltage. Notice how I have the ammeter set up with only one test lead in the common port, and I have my meter functioning as an AC ammeter, and therefore I push the ACI button, right? So the ACI button is going to give me my AC current. All right, so if I want to measure the inductor current down here, if you remember, that inductive current was around 460 milliamps when measured with the power analyzer. Okay, now remember, I left that port open on the AC ammeter for a purpose, because my circuit connection for a purely parallel circuit is just going to move from the circuit up to there. So that means I'm just going to connect it directly to there on the AC ammeter. And now I'm going to take my black lead from the ammeter and connect it to where I removed that from. Right? So now that means that I've got my inductive branch current only. And if I look up here at the display, you can see I have that 456 or 460 milliamps of current for that branch, right? So if I wanted to measure the resistive branch, that would be no different, right? I would just remove this, connect it back to my inductor. I'd take my resistive branch and connect it to my AC ammeter, and I would take my black lead and connect it to the ammeter, and that's going to give me my AC amps for my resistor, right? Okay, so what does that look like if I just return the circuit to its original condition? I remove where my ammeter was, and my circuit is back to a parallel circuit. Okay, so that's the way you use the desktop ammeter to measure AC current. But what do you have to remember? The LFR rule, right? Make sure the leads are in the right places. Use only the 10 amp location on the ammeter. Make sure it's functioning as a AC ammeter by pushing the ACI button, and you'll be able to measure branch current or total current in a series circuit. Okay?